Vehicle of a mass of 1,000 kilograms. Suspension with a stiffness of 40 kilonewtons per meter and a damping coefficient of 2.3 kilonewton seconds per meter. Okay, is driven over a road which gives a vibrational input which can be characterized approximately by a constant spectral level of 0.1 g squared per hertz. Okay, so again, I've got this power spectral density. It's a constant, and I've been given the value in this case. Find the RMS or root mean square vibrational acceleration level of the car. So this system can be modeled as a mass with a base excitation. Okay, my input in this case is xb, okay, or x double dot b, and my output is going to be x, or x double dot. And between the two, I've got a spring and a damper. I've got the value for the spring, got the value for the damper, I've got the value for the mass. And so my equation of motion, okay, mx double dot plus cx minus x dot minus x dot b, okay, so you've got the relative velocity between the two, and here we've got a spring system, so it's the relative displacement between the two. You can rearrange it, putting all the x's on one side and the xb's on the other side to get that equation, and then to divide, you can make the substitution in here, and then you get the output divided by the input will be your h term. And so there's the substitution in there. The exponentials will cancel out because they're the same on both sides. Okay, and I take my output, which is my x, divided by my input to give me this function, and that is the complex frequency response function. So the power spectral density of the car, the motion of the car, and like I said, we're talking about the acceleration, so it's x double dot. It's going to be my complex frequency response function, magnitude squared, times by the power spectral density of my input. Now, so obviously I can go through the process. My expected mean square value is going to be all of this lot. Okay. So here's my output. The integral of the output will give me this thing, but obviously the output equals this lot here. Okay. So there's my input power spectral density. There's my complex frequency response function. And like I said, this term was a constant, so that can come outside, which is here. Okay. And you can solve it. I've solved the integral first, but basically this is our identity. Okay. In this case, we've got these terms for A, B0, B1, A1, A2, and A0. And so you can replace those terms in this equation. Okay. So that's what we get. So we get k squared upon k, because B0 was k and A0 was k. So we get k squared upon k, so that's just k. A2 is m. B1 was c, so we get c squared over here divided by cm. And so you end up getting m times k plus c squared upon cm times by pi times by my power spectral density, my input. Now, like I said, I was given power spectral density, this term, in g squared per hertz. Okay, so that's my single-sided function in terms of frequency, in terms of frequency which is in hertz. To get it in terms of omega, which is in radians per second, I have to divide this by 4 pi. So it's 0.1 g squared divided by 4 pi, and then that will give me g squared per radians per second. Okay. So I take that term, my 0.1 divided by 4 pi, I stick it in here. There's my g squared. I don't lose that. Then I've got my the integral of that frequency response function. I now therefore have an equation for mean square, so I can plug in the values. I get 0.49 g squared. Take the square root of 0.49, which gives me my RMS value, which is 0.7 g. Okay, so the root mean square, the measure of the magnitude of the varying quantity, okay, is 0.7 g.